Hello everyone, welcome again in Eng-Man YouTube channel. So today we will use WellFlo, and the case is again about workover. In this workover, I'm planning to perform perforation addition. Okay, I will just add perforation at the same reservoir. So I will expect that the skin due to limited entry or skin due to partial penetration will be reduced because I add perforation interval, and because the skin will be reduced, I expect the productivity index to be improved. Okay, so this is the current condition of the well. In WellFlo, the WellFlo dashboard, you can see. Okay, let's check well and flow type. It's an ESP well, flow through the tubing, of course, fluid type black oil. It's a vertical well. Okay. And then for the flow correlation, I use Duns and Rose with well and riser L factor 0.95. Okay. Reference depth onshore. Okay. And then zero depth at the Kelly bushing or rotary table. And the distance between Kelly bushing to the wellhead is 15.32 in feet. Fluid parameters. Okay, let's check the fluid parameters. Here you can see the API gravity is 36. So the oil specific gravity will be 0.84, and then gas specific gravity 0.7. Water salinity 17,000. Okay, 17,000 ppm. Okay, water gravity, so it will be calculated accordingly. And I use Glasso equation for the bubble point pressure estimation, the GOR, gas oil ratio, and then the oil formation volume factor. For the oil viscosity, I use Beal et al., gas viscosity Carr et al., and surface tension, I use advanced method. Okay, I can input the reservoir pressure and then reservoir temperature and then the produced GOR being 300 SCF per STB. I can click calculate and I will get the bubble point pressure and then oil formation volume factor and the rest of these parameters you can see. Okay, so this will be the background. All right, and then let's go again. You can check the chart, plot, if you want to see the gas viscosity, if you want to see the gas Z factor, okay, and then oil viscosity, okay, using the WellFlo. Okay, again, to make it clearer, in WellFlo for the fluid parameter analysis, you just input the oil API gravity and the specific gravity will be calculated, or you input the oil specific gravity and the API gravity will be calculated. The same thing with water salinity. If you input water salinity, then water gravity will be automatically calculated, and vice versa. If you input the water gravity, water salinity will be calculated. Gas specific gravity, you just input, and then you select the correlation that best describe your fluid. Okay, in this case, I used these correlations. And I input the inorganics, H2S, and then CO2, and then nitrogen. Okay. And then for the PVT data calculator, I input the reservoir pressure, I input the reservoir temperature, and I also input the produced gas GOR. And I click calculate button, and then I will get the estimation for the bubble point pressure, oil formation volume factor, oil viscosity, oil density in pound per cubic foot, sigma oil. This is the interfacial tension, okay, from this sigma, from the oil, I mean, and then this is the solution gas GOR, solution gas oil ratio, gas formation volume factor, gas viscosity, gas density, water formation volume factor, water viscosity, water density, and again, the interfacial tension by the water. Okay, so all of these parameters you obtain from the input and from the selected correlations. If you change the selected, if you select other parameters or other correlations, then you will have different results. Okay, if you want to see the chart, you can just go from check to chart. And here you can set the upper and lower range. You can set the steps. You can set the temperature range if you want. Okay, the upper side is the pressure range. The lower side is temperature range. And then you can open the drop-down menu. You can plot gas viscosity, gas Z factor, produce GOR, oil viscosity, and I want to show the oil formation volume factor. After selecting this parameter, you can skip these ranges, click plot, and you will have the chart. Okay. You can open the table. Okay, so you can get the numbers here. All right. So this is the fluid parameter analysis or fluid or PVT analysis. Quite simple in WellFlo. All right. So again, we will go to the reservoir. This will be our main subject. So currently I have this IPR calculator. Okay, the name of the reservoir is BRF. This is the reservoir pressure, reservoir temperature, middle perforation at the current perforation interval, but I think I need to change it. Okay, wait a minute. Okay, so the current mid perf is at 2,954 feet, water cut 97%, and then gas oil ratio 300 SCF per STB. I generate the IPR using Vogel equation by inputting the well test data. Here I input the pressure at the pump intake. So it is the pump intake pressure, 161.7 PSIA. And the flow rate I get is 526 stock tank barrel per day. So the WellFlo will extrapolate from the pump intake pressure down to this one, bottom hole pressure. So the bottom hole pressure is 194. Okay, using the selected Vogel equation and the well test data, WellFlo calculated that the productivity index J or is 1.1392 or 1.14. So that the absolute open flow, the maximum flow rate is 570 stock tank barrel per day. You can generate the IPR here. Okay. So the flow rate, the well test is here, and this is the IPR. So you see, we already produced the well at optimum condition because the flow rate, the existing flow rate is more than 70% than the of the maximum flow rate. So it's already at the limit of this well. So if you want to get higher production rate, you need to perform workover. And in my case, I will add perforation to reduce the skin and to increase the productivity index. Okay, before that, I will create an analytical model first. So this is the actual condition. I need to create an analytical IPR that will mimic this actual condition. Okay, so I will add reservoir or add layer, and then I will call it match. Okay. So the reservoir pressure is 914.7, temperature 180. By the way, I will use analytical, so I select layer parameters. Okay, layer parameters. And in this IPR, analytical IPR, I will try to achieve the same productivity index. Okay, so that the analytical will be the model of the actual condition. The actual condition, the IPR is generated using well test data, but here I will generate the IPR, analytical IPR, using reservoir characteristics. Okay, and then I need to input the middle perforation to 954. Permeability based on well log data is 134. Okay, later on I will adjust the permeability to get the same productivity index. Okay, so I will adjust the permeability to match the actual condition. Yeah, you can either adjust permeability or thickness or both of them. But in this case, I have more uncertainty in the permeability, so I will adjust the permeability. The thickness being 56.5, Wilbur radius 0.4. Okay, 0.4 in feet. Okay, and then relative injectivity 0, of course, because it is a production well. Okay, let me check again for the wellbore radius. Wait a minute. So it's 7-inch casing. Okay, 7-inch casing. So the hole will be 8.5 inches. So I will divide. Okay, so the wellbore radius should be 0.354 to be more exact, or 0.35. Okay, water cut 0.97, and then gas oil ratio 300. I will construct the IPR using Vogel equation with Vogel coefficient of 0.2. And of course, I will include calculated skin because I will have skin due to partial penetration in my actual condition. Okay, and drainage area geometry, I assume circular drainage shape with drainage radius of 250. This is another assumption actually, but it is a good assumption if you are not certain about the boundary of your well. Okay, if you don't see any clear geological boundary, okay, or stratigraphic boundary, then 250 is a rule of thumb for an oil well. Okay, and then the skin, completion type, case hole. I don't know for sure about damaged skin. You need to perform laboratory to know that. So I will skip. I will not input the damaged skin because at the end of the day, I know that limited entry skin will be much bigger than the damaged skin. So we can say damaged skin can be negligible. I include limited entry skin. I include deficient skin, perforation diameter 0.37. Okay, and then shot penetration in inches 39.6. Shot density 5, shot facing 60 degrees. Okay. Now the nearest measured formation distance. I check the log data, okay, and then I calculate the distance between the top or bottom perforation with the top or bottom boundary. and the nearest distance is only 16.88 feet. Okay, so it's quite close, 17 feet. Vertical permeability, I don't know for sure. Yeah, because maybe my laboratory data is limited, but I can make a guess. Usually, or not usually, I think it's quite a general prediction that the vertical permeability is more or less 10% of the horizontal permeability. So if the horizontal permeability is 134, vertical permeability 13.4. Sorry, horizontal permeability is 134, vertical permeability 10% of that, so it is 13.4. Currently, open interval is 16 feet. So you see the limited entry skin is 10. Okay, 10. Yeah, 10. Skin is dimensionless. Well deviation is 17 degrees. So there will be negative skin. Okay, because deviated condition will give a bigger, okay, a larger flow area. So the skin will be negative, but it is not big. And then perforation skin minus, okay, minus, but if you change to, for example, Tarik equation, it will be positive. So yeah, but the magnitude is not too big. So so in the end, the limited entry skin will be the dominant skin factor. Okay, so far so good. So you see, yeah, at this point I can save. Okay. So as you can see here, I get productivity index of 3.55 or 3.56 or 3.6, which is bigger than the actual productivity index. If we go back to test data, the productivity index is 1.139. Okay, so if I go back to the analytical IPR and the layer parameters, I need to change maybe one parameter so that I can achieve productivity index of 1.13. Okay, I can reduce the permeability, I can cut the thickness, okay, or maybe I can add damaged skin, okay. Let's say I will add damaged skin, but yeah, if I input damaged skin, then I need to justify the damage zone permeability and damage zone thickness. I don't know both of them. Okay, so it's quite, yeah, it can be problematic. I can reduce the drainage radius, for example, 100. Oh, sorry, I can, if you decrease the drainage radius, actually the productivity index will increase. So let's say 300, but changing the drainage radius will not impact much. So I think the safest approach is to maintain at 250. What about decreasing the vertical permeability? Let's say to be 5%. So it's 6, for example. Okay. Again, the productivity index will not be significantly changed. So I will maintain at 10%, but the permeability I can cut down to be, for example, 100. You see, so productivity index decreased to 2.8. Let's say 90, but I also changed the vertical permeability to be 10% of it, 9. Now it's 2.3. Okay. Or maybe I can just maintain 134 and 13.6 and 13.4, and maybe I can insert calculated skin. Okay, I can input measured skin directly, for example, 2, it will be reduced. And then 3, 5, 6, okay, and then 7, 8, 10. It's quite dangerous because the skin is too big. All right, so you see, you need to increase, to input the skin to a very big number to cut down the productivity index. So I'm not sure about that. I will go back to 0 instead, and then change the permeability instead to 80. And this will be changed to 8. Okay, not enough. Let's say the thickness. Maybe I can cut the thickness down. Okay, thickness, I can use another estimation. Actually, I can use the thickness to be only 25. Okay, doesn't change significantly. Okay. Okay, 50, oh man. It's quite dangerous. Maybe I can just cut down to 70. Okay, and then the vertical permeability to be 7. And then I will add the measured skin to be 4 or 3 or 2, 1.3. So I will increase 2.5. Yes, sometimes you need to change it manually like this, 1.17. I will check again this 1.14. Okay, 1.14. Okay, 1.14. And then, okay, I will increase to 3.1, 1.16, 3.2. Okay, maybe 3.3. Okay, so now by changing the permeability, okay, to 50% of the initial data from the log, and then by adding the measured skin, I can achieve productivity index of 1.13. Okay, so I can save at this point. Okay, and then yeah, this is the deviation. Okay, now I will check the show composite IPR. Okay, we have a problem. Mid perf 2954. If we go back to this one, test, still invalid test pressure, invalid test rate. The test pressure should be greater than test pressure. I think it's already correct. Okay, what about this one? Oh, maybe just to put something here. Yeah, It's a software problem. Actually, I will not use the test data for my analytical IPR, but okay, 161.7.526. Okay. Okay, so I can apply, but actually I will use this layer parameters. Oh, this one, BRF invalid drainage area. Invalid wellbore radius. Formation thickness should be greater than 0, of course. Oh, I think the problem is here. Okay, yeah. In this section, I actually don't use this one, but I need to input all the data. Okay. Okay, but I will change to the match analytical IPR. Okay, so I can save. All right, now I can show the IPR. Yeah, okay, I know. We cannot use this one. This one is the composite by adding the BRF and matching, and this one is from this legend. Match Fogel, this one, and then BRF Fogel. Okay, we cannot use this one. Okay, back to the first discussion. So now we achieve the same productivity index, the same absolute open flow between the actual IPR, which is here in BRF, and the match or the analytical IPR. I constructed with using the reservoir characteristics and well configuration, perforation configuration. So I will use this analytical IPR to estimate the improvement of productivity after I conduct workover. Okay, workover. So I will maintain this analytical IPR and I will change the perforation configuration after the workover so that the skin will be reduced, skin due to partial penetration will be reduced, and I will get increased productivity. Okay, so I will add another layer and I will call it after job or after workover. Okay, after workover, let's input the pressure, the temperature, the mid perf. Now, after I add perforation, the mid perf will be located. Okay, wait a minute. So I need to calculate it first. Okay, so I will add perforation at the upper section. Okay, so if we can go to the dashboard here, all right, here is the current perforation. I will add the perforation at the upper side, but still at the same reservoir. Okay, so I will add perforation interval. The length of the perforation interval will be increased. And yeah, I will decrease the skin due to partial penetration. So I go back to reservoir, and the new middle perforation will be located at 2937. Okay, previously 2954 with the same permeability to be 70 millidarcies, okay, based on the match IPR and thickness of 56.5, wellbore radius 0.354, water cut 0.97, and gas oil ratio of 300, Vogel coefficient of 0.2, drainage area 250, circular, and then I will input the calculated skin, go to the skin, case hole, limited entry skin, deviation skin. I will input the perforation configuration, 0.37, measured shot penetration 39.6, shot density 5, shot facing 60 degrees. I will calculate with Tarik equation, the same with the previous calculation. And now with the added perforation, the nearest measured formation distance is only 3.45. So it's now much closer to the distance of the boundary, or to the boundary. Okay, to the upper boundary of the reservoir. And vertical permeability 7, just like before. And now the open interval is quite long, which is 46. So I add 30 feet. Okay. Now you can see limited entry skin decrease significantly. Previously it is 10. Now it is only 0.87. Okay. So by adding perforation, by adding 30 feet, in addition to the existing perforation interval, I will decrease the limited entry skin significantly, so that you can see the productivity index now increase from 1.13 to 4.2. Okay, but of course I need to input the well deviation to be 70 degrees. Okay, and then measured skin, I will assume that the measured skin will be 0. Okay, previously it is 3.3, but after workover, okay, I will add perforation and I will do well clean up, and then I will produce. I expect the measured skin will be 0. I expect the wellbore will be cleaner. I expect the sand face will be cleaner. So I can cut down the measured skin, previously 3.3, now it is 0. But I can also input 3.3, and you can see productivity index will be reduced to 2.76. But I want to be more optimistic. I will cut down to be 0. As something like this, you need experience to make the justification. Okay, so I will click apply and then click save. And I will check this one. Yeah, previously in the match analytical IPR, the open interval is only 16, but after walkover, I add 30 feet additional perforation. Now it is 46. So now I can plot the composite IPR plot. I will not use this one because this is actually IPR that is generated by summing up all the IPRs. We will not do that. We will not do commingle reservoir here. We just change the productivity index by adding perforation. So to avoid misleading, I will make it white, and then I will change the scale maximum to be okay. So legend BRF for gel. So this is also cannot be used because if we go back to show layer data and then we go back to BRF, here you see the productivity index is 8. It is not correct because actually the for the BRF, the IPR is not based on layer parameters, but based on test data. Okay, test data. Okay, so this should okay, so it should not be this big, but if I go back to test data, the productivity index is actually 1.13. Okay, so okay, again show composite IPR. I will make this one to be white and also this one to be white. And then change the properties to be okay. Okay, so this one is IPR after walkover, and this one is the analytical IPR, which is already matched with the actual IPR. So as you can see, by adding perforation, I significantly increase the productivity index and the IPR becomes better. Okay, so go back to here. So that's the conclusion. So now we can say, we can be confirmed that by adding perforation, we will reduce the skin due to partial penetration or skin due to limited entry. And yeah, we will improve the productivity index and get bigger or higher flow rate. Okay. And the next one is, of course, to perform nodal analysis, but I think I can close right now. Okay. Thank you. I hope you enjoyed the video. I hope this video is useful. Thank you so much for watching and see you again in the next WellFlo videos. Thank you.